Okay, so let's consider again our infinitely large plane, and we're looking at it in cross-section of charge density, let's say sigma, and another plane, another infinitely large plane of the same charge density, sigma. So let's put a few plus signs here indicating the positive charge density on that plane, as well as on this one, uniformly distributed. Let's find the electric field everywhere in space. So the top plane produces an electric field which will indicate with blue arrows. So above, the field points upwards. So here are a few field lines indicating that field, and below, the field points downwards, and it has the same magnitude. So the arrows are all of the same length, whereas the bottom plane produces a field which below is in the same direction as the other field. It's away from the plane, so it's downwards. Above that, it's this way. It's pointing above. And here, the same thing. So we can see from the different colors that the electric field, the net electric field, here is going to be the sum of the two electric fields, which we know, as we've seen before, is equal in magnitude to the charge density sigma over 2 epsilon naught. Of course, it's n hat. It might be, well, let's just leave it like that. So we have to add two of those, right, because we have the red and the blue, and so we get a net field which is charge density over epsilon naught, pointing away from both planes, right, pointing upwards. And here we can see that the fields are equal and opposite, so the net electric field in there is actually 0. And we get the same thing here, except the electric field is downwards, but I guess we could use the same symbol. N hat means just normal to the surface, and normal to the surface down here means downward. If we used, x, y, z coordinates, we could say that the electric field above the planes is sigma over epsilon naught, say k hat, if we decide that's the z direction, and the field down here would then be sigma over epsilon naught minus k hat, so it would look like that. So we have an electric field that's constant everywhere, but it's 0 in between the plates. So now let's consider something similar, but the two infinitely large surfaces have positive charge density sigma and negative charge density sigma, so we would make minus signs here. Now what do we get? So let's draw the field again in blue produced by the positive charge. So up here it's pointing up. The arrows are all the same. Here it's pointing downwards, and the same down here. And the negatively charged plane produces a field that above here is pointing downward, right? It has to point toward the charge, the particles, and they're negative, so the field there is pointing downward. The same thing is true here. Whereas here the field points upward, and what we see, all the arrows should be of the same length, what we see is that the field up here is 0. The same is true of the field down here, because equal and opposite electric fields, whereas the field in between is, let's use a coordinate system in which this is the z direction. So we get an electric field which is sigma over epsilon naught. It's vertical, but it's pointing downward, so it's a minus sign. So this is a way of getting a strong electric field between the plates and the zero electric field outside. And so as an approximation, if we have two finite plates with equal and opposite charge, then we'll get an electric field inside, whereas you'll have an electric field out here that's everywhere zero, not equal to zero. And so it should not really surprise us that when we get to electric circuits and we consider the energy that's stored in an electric field, we want something like this, where we don't have a strong electric field everywhere else around us, but it's localized.